Now that we have learnt some fundamentals about wind, including speed, direction, units, and coding, let's examine some specific winds and the forces involved. The first of these is the geostrophic wind. As with most concepts and theories, a combination of assumptions and facts govern the understanding of this phenomenon. These help us to simplify the complexity of reality and help model what is actually happening. Two winds. Firstly, we will explain and list the facts we know about the geostrophic wind and expand on each one as mentioned. The geostrophic wind is composed of two forces. These forces must be in balance and work opposite to each other. What are these forces though? The first of these is the pressure gradient force or PGF. Looking at the diagram, we can see this is the force that acts from a high to a low pressure. How can we judge the strength of this force from a chart? Just like controls on a map showing us terrain gradient, isobars tell us the pressure gradient. Closely spaced isobars tell us that the pressure gradient force is strong. This is common in low pressure systems. Widely spaced isobars tell us that the pressure gradient force is weak. This is common in most high-pressure systems. But what is the significance of large or small pressure gradient forces? The pressure gradient force is what determines the strength of the wind. If the pressure gradient force is very large, then there will be a rapid movement of air, and the resulting winds will be very strong. However, if the pressure gradient force is very weak, then the air will move slowly, resulting in light winds. In summary then, closely spaced isobars show large pressure gradient forces and therefore strong winds. This is typical in most low-pressure systems. Widely spaced isobars show weak pressure gradient forces and therefore light winds. This is typical in most high-pressure systems. On most surface pressure charts, the correlation of isobars spacing, pressure gradient force, and wind speed is quantified for us by the use of a scale. This scale is called the geostrophic wind scale. An example is shown here. If we measure the isobars spacing and use the geostrophic wind scale relevant to that latitude, we can calculate a wind speed. Here we have measured the distance between isobars near a low pressure. Notice the close spacing and fast wind speed. On this second example, we have measured the distance between the isobars near a high pressure. Notice the wider spacing and resulting slower wind speed. That completes our coverage of one of the forces involved in the geostrophic wind. The other force which acts opposite to and balances the pressure gradient force is the Coriolis force. What is this force? It is rather complicated and in fact not really a force as such but rather an apparent force. This apparent force is due to the rotation of the Earth. The best way to explain its nature is to go through a diagrammatic explanation. The image shown here is seen from an observer looking down on a North Pole. We are going to compare 2 points on the Earth. One of these is that the equator, shown here, and another at 60 degrees north, shown here. As the Earth goes through one rotation, these 2 points return to their original positions within the same time period. But if we compare the distance that these two have traveled, then we see a significant difference. The distance that the point on the equator traveled was 21,600 nautical miles, whereas the point at 60 degrees north only traveled half that distance. Yet they completed this in the same time. This has an important effect. It means that the point on the equator is traveling faster in space than the point at 60 degrees north. If air were to flow from one location to another, it would find the surface underneath it traveling at different speeds. The best way to demonstrate this is to use this example. If an observer was standing at 60 degrees north and he attempted to throw a ball at an observer on the equator, the effect would be as shown here. Notice that the ball never reached the intended target. In fact, it has fallen to the right of the intended target. Wind will behave in exactly the same manner if it tries to flow from the 60 degrees north position towards the equator. We can therefore suggest that due to the rotation of the Earth, the wind has been deflected to the right as it has traveled along the surface. In the northern hemisphere, we can say that the Coriolis force acts at 90 degrees to the right of the wind. In the southern hemisphere, looking down on the South Pole, the effect is reversed. If you watch the animation, you will see the ball this time being deflected to the left of the intended target. So, in the southern hemisphere, we can say that the Coriolis force acts at 90 degrees to the left of the wind direction, causing it to be deflected to the left of its intended track. The difference in speed between two fixed points is greater nearer the poles than the equator. Looking at the diagram, we can see two locations near the equator. These 2 points will have only a small difference in speed, but the 2 points nearer the poles will have substantial speed differences. Therefore, the Coriolis force is said to be greatest at the poles and nil at the equator. However, the magnitude of the Coriolis force within 15 degrees either side of the equator are so small, we actually consider the force to be nil within this zone. But if you remember from earlier, we stated that the two forces of the geostrophic wind must be in balance, namely the pressure gradient force and the Coriolis force. However, we have just learnt that within 15 degrees of either side of the equator there is no Coriolis force. Therefore, there is an imbalance of the forces. This prevents us from calling any wind within 15 degrees of the equator a geostrophic wind. Consequently, we must theorize another wind, which recognizes the fact that there is no Coriolis force within this latitude band. It is not necessary to go into its detail within this lesson. It is sufficient to say that all winds within 15 degrees of the equator are called antitryptic winds. There is one more point to learn about the Coriolis force. The condition that creates the Coriolis force, that is, the rotation of the Earth, is always present. However, the effects of the force, that is, the deflection of the wind, depends upon the speed of the wind. A high wind speed results in greater observed deflection. If there is no wind, there is no observed deflection. As a result, we can say that the Coriolis force is proportional to the wind speed. This completes the explanation of the two forces involved in the geostrophic wind. But there are other points about the geostrophic wind which need to be considered.